Okay? So that's how this problem is solved. Now, you just have to be careful. Also, this definition is very simple, but when you plug in the numbers, just be careful that you always remind yourself that when you are considering one object, just focus on the object. And the mass has to be individual mass. So for the first part, when you are considering the bar, always remind yourself that you have to use the mass for the bar. Don't use the mass from the disk. And the same thing applies to the disk. All right. As you can see that in this example, calculation is not difficult, right? All we have to do is to use parallel axis theory, and you can calculate the mass moment of inertia of any complicated objects. Now, let me ask you this question. What if I change this point of rotation? What if I moved what if I change the boundary condition from this point O to maybe to this point? What if we do that? Let's say we don't want this thing to move like this. And we change the boundary condition. We want this thing, this pendulum-like object to spin with respect to a new point. And so let's call this one O prime. We do that? Of course, we can do it, right? Now, when you make this change, you look at the definition here. Whatever the point you want to consider, it must be the summation of mass moment of inertia at the center of gravity plus m times d squared. Now you know that for the first term, the mass moment of inertia at the individual objects, this value Ig will never change. Correct? It will never change, no matter you consider rotation at this point or you consider rotation of this point. The center of gravity for the bar is always at the center of geometry. And the center of mass for this disk is always at the center of its own geometry, which means the Ig value, the first term that you calculated before, is always this value. This will never change. Correct? So that tells you if I change the point of rotation from this point to this point, you will still use the first term, which is the Ig. The Ig will always be this value. The only thing difference is what? Is the distance here. That's the only thing going to change. All right? Questions? Is that clear? Yes, Mike.
Question for you. So in strengths of materials, we also learned this equation, but it wasn't with mass. It was with area.
Mm-hmm.
And the final units wound up as length to the fourth. Is that related to this, or is it two completely separate
It's
moments of inertia?
Yeah, that's moment of inertia, but that's not mass moment of inertia.
Okay, so this is mass moment of inertia.
Mass moment of inertia is not moments of inertia.
Okay.
So for moments of inertia, you will use it in not strengths of material, but also reinforced concrete, steel structures, and all different kind of mechanics courses. Moments of inertia is in the unit of length to the power 4. But mass moment of inertia is kilogram times length squared. Let me see this.
Okay.
Yes.
Okay, cool.
Length squared. So these two are different things.
Okay, awesome. Thank you.
Sure. Any other questions? All right, good. So let's move on. Next, we are moving to the next topic, which is planar kinetic equation of motion. And this part is on my notes, page 45. if I'm not mistaken. Or it's page 46. It's from page 46 to page 48. This part is from page 46 to page 48 for planar kinetic equations of motion. Okay, so what is this subject about? Remember we talked about earlier that in dynamics we consider different types of motion. We consider that first of all, if you have an object which is so small that we don't even consider its volume or its size, that means we only consider this as a point or the particle. In that case, you can use rectilinear motion or curvilinear motion to consider that. So before, you do not consider any geometry effect. It's just a point with mass. Whether it moves linearly or it moves non-linearly, doesn't matter. So that's what we were before, remember? It was probably the first month. And then we start considering geometry. This was at the beginning of March. Now we start considering the size effect, which means the motion of a ball is different from the motion of for example, maybe a cylinder. When there's angular motion involved. If it's linear motion, that means if everything moves without any angular motion, then you can define the center, velocity, displacement, acceleration as the same velocity, displacement, and acceleration for the rest of points on this object. In other words, if for this ball, if it's moving along the straight line, the displacement SG, VG, and AG at the center of gravity is the same value everywhere else. That's what we know. So this is the part we call the rectilinear motion. Now we are no longer consider just a particle, we consider a sizable objects. That means you have to consider geometry. It is also the same thing. If you have a cylinder and the cylinder moves horizontally like this, there's no spinning, no rotation, then the center velocity, center displacement, center acceleration is the same of the velocity, displacement, and acceleration everywhere else in the cylinder, as long as there's no rotation, correct? Now, what if there's a rotation? And this was the subject we talked about since March. What if you have translational motion, but also rotational motion? So it's not only moving this way, but it's also spinning like this. When this happens, the statement I just made about the representativeness of displacement, velocity, acceleration at the center of gravity for the rest of points on the same object will no longer be true. You can no longer use SG, VG, or AG to calculate velocity, displacement, acceleration everywhere else. You will have to consider, that's what we call angular effect. And that's the part we start considering the conversion, remember? How do you convert linear parameters to angular parameters? And this is the part we said we have S, we have V, and A. And how do you convert it back and forth to theta, omega, and alpha? Right? So what is the problem in planar kinetic equations of motion? In planar kinetic equation of motion, we are concerned about this kind of problem. Suppose you're provided with a shape with arbitrary geometry. in any case, you can always define the center of mass. Now, of course, if this is irregular objects with non-uniform or uniform mass density, that doesn't matter. You can always find the center of gravity, which is right here, right? Now, suppose you also know, you have everything you want to know. At the center of gravity, you have the displacement, of course, has to be a vector, SG, BG, and AG. Like this. And of course, at the same time, we also consider the angular motion. So this whole thing is not just moving linearly, but also subjected to angular parameters like omega, alpha. Now we have this too. So what's the problem? The problem is this. Sometimes in the what we call unconstrained motion, say if you are trying to throw an object, in this case the eraser, from here to the floor, and when I placed the eraser horizontally, it's going to drop horizontally because the center of the mass is at the center of gravity, and when you applied a linear motion, in this case the motion is driven by gravitation, as you know that, of course. Now, if I'm actually spinning this object, say I'm moving it at the angle and also spinning like this, so it will move with respect to the center of gravity, right? If I do it again.